Hello everyone. In this video, we are going to see how to construct the DC motor using a Laplace using a transfer function. The block diagram of the DC motor is given here, in which this is the gain of the electrical circuit, that is armature circuit, and this is the gain of the mechanical system. We need to construct this block diagram in order to construct the DC motor. So to construct this machine, to construct the DC motor using a block diagram, we need two summing point to gain two transfer function blocks, and then we need gains, everything. So let us now construct the block diagram. So we need summing points. So let us take summing points. We need two summing points. So let us drag the summing point to get the another summing point. The summing point, it is having 1 plus and 1 minus symbol. So let us change the signs as plus and minus. And to the plus, we need to keep the input voltage. This voltage can be given with the help of a constant block. So let me take a constant block to feed the voltage, and let me take the voltage to be 200 volt. So we will connect this to the plus sign of the summing. And we need a transfer function block. So let us type a transfer function. So here, the numerator of the first block, it is having 1, and the denominator is LAS plus RA. We know that LA value is given as 0. So we have the parameters of the DC motor, which are given here. The denominator, in the denominator, the first coefficient is the LA. So let us substitute the value of LA, 0.9134, which is given as LA, the given parameter. And then we will have the RA value, which is also given in the parameters, which is 0.634. So we have this transfer function, and let us connect this to. Let us connect this block to the output of the summing block, and then we have a constant block. Not a constant block. We have either we can use a gain block. We can use a gain block because your KT is nothing but the gain of the that is a constant, which is star constant, so which can be represented with the help of a gain block. So whose value is given as 0.127. So 0.127. This is the gain, that is a torque. This is the torque KT. And the output of this KT is given to another summing block. And we have again the transfer function of the mechanical system, which is represented as 1 divided by Js plus B. The value of J, it is given as 0.9058, and the B value is given as 0.8147. So we can represent the numerator function as it is 1, and in the denominator your J is whose value is 0.9058, and the B value, it is given as 0.8147. 0.8147. So this is the second transfer function block, and the output of this block will be the angular speed. And then we have one more gain, which is nothing but the back EMF of constant KB. So either we can track this or we can connect a new one. We will press Control R to rotate the gain block, and then we'll connect that to the output of the second transfer function, and we'll connect the gain, another output terminal of the gain, to the first summing block with the minus sign. And the back EMF, it is given, the back EMF constant is given as 0.1 vacuum of constant is given as which is also same as the torque constant 0.127. So we can have the same value, and we need to have the load torque. Let us have the load torque as say, for example, initially we will take the load torque as 12 Newton meter, and then we will do this. Now here we have the omega, that is angular speed. So let us we can, if we want to this is the angular speed which is given here, and if we want to convert the angular speed into RPM, then we can convert that by, we know that the omega is equal to we can write n, that is speed in RPM, equal to 2 pi. Yeah, that is we can write the angular speed equal to 2 pi 2 into 2 pi n by 60. This is the angular speed. Angular speed is omega equal to 2 into pi into n into n divided by 60. So from here we can convert the omega into n by multiplying this omega by 60 divided by 2. 60 by multiplying the omega by 60 divided by 2 pi. That is so we can have the gain as 60 divided by 2, which is 30. So 30 by pi. That will give the speed in RPM. So this is 30 by pi. Now we can see the output with the help of the display. Or we can also see the speed waveform with this scope. Now we can run this. So if we run this, we are getting the speed in RPM as 317.8 RPM. So which is the this is the speed waveform in RPM. We can also see the speed in the angular speed omega, which is coming as 33.228. So this is how the DC motor is constructed, and the waveforms of the speed in RPM we have seen. Thank you.